I'm going to be covering section 4.5, sketch of a curve, where we're going to use derivatives and second derivatives to sketch complicated graphs of functions. So the first thing you're going to look at when sketching a graph of a function is the domain, x and y intercepts, asymptotes, and symmetry of the function. So domain, where x is defined. X and y intercepts, you're looking at where it crosses the x and y axes. For asymptotes, you're just going to see where the graph is defined. And symmetry, that's looking at if the function is reflecting over the x or y axis. And that you can test for by plugging in a negative x. So if you have f of x, then you plug in a negative x, and you get a negative f of x back. So basically the function except negative. That's going to be odd with symmetry in respect to the origin. If you plug in a negative x and you get f of x back, same exact thing, that's even, and that will have respect to the y-axis. Okay, the next thing we're going to look at is intervals of increase and decrease. So in this step, we're looking at where the function is going up and where it's going down. And to figure that out, we can use the first derivative of f of x, because we know that the first derivative of a function tells you what the slope is at any given point. So it makes sense that if we figure out where that function is negative or where that function is positive, we'll be able to tell what the graph is doing, like if it's going up or down at that point. So to do this, you find the derivative, set it equal to 0, and then what you do is solve for x, and then your x values, so you get a and b, those are going to be your critical numbers, and any other critical numbers will also be if there's any values at which the derivative of f of x is not defined. So if you have critical numbers of a and b, you're then going to set up an interval on which to test. So you set it up negative infinity to a to b, and b to infinity. And then test a value on each one of these intervals and plug that value into f prime of x, and then look at the sign of the answer that you get. So say you got negative, positive, and negative values back. That would tell you that the function is decreasing on this interval and increasing on this one, and again decreasing here. Alright, so the next thing we're going to look at is the local maximum and local minimums of the graph. So that's looking at where this graph will either go have a minimum or a maximum. And this we can figure out by looking at the information we got in step 2, so looking at where it changes sign. So if we look at here, we see that it's decreasing here and then it goes to increasing at point A. So that tells us that a comma f of a is going to be your local minimum. Then if you look here, you see that the slope is increasing, and then at b it starts decreasing. So that tells you that b comma f of b is going to be your local maximum. Okay, so the last thing we're going to look at before actually sketching the graph is the concavity and the points of inflection of the graph. So to find the concavity of the graph, it's very similar to how we found the intervals of increase and decrease of the graph, except now we're going to do the same thing with the second derivative. So you find the second derivative of f of x and set it equal to 0, and then you solve for x, and those values are going to be your critical numbers, as well as any values at which the second derivative of x is not defined. Then again, we're going to set up intervals. And then once we have those intervals, we'll pick a value on each of the intervals and plug it into the second derivative of x and look for the sign. So say once we plug that in, we go positive, negative, and positive values for each of these. So a positive sign here tells us that it's concaved upwards, so that looks like that. A negative sign tells us that it's concave downwards, so something like that. Not even like just generally curved downwards, and again concave upwards. So then from this, we can find the points of inflection, which are where the concavity changes. So if you think about a graph, and it goes like that, there must be a point on there at which the concavity of it changes, where it goes from being concave upwards to concave downwards. And we can find that by looking at the values of c and b. So here we see that it's concaved upwards, and then it goes to being concaved downwards. So that would be something like this. So we know at c there's a point of inflection. And then there's also a point of inflection at d, because we see that it goes from being concave downwards to concave upwards. Alright, now I'm going to do an example problem. Hopefully that helps. The problem that we're going to be doing is f of x equals x minus 3x to the 1/3. Super fun stuff. Okay, the first thing we're going to do, look at domain x x and y-intercepts, symmetry, and asymptotes. So looking at this, we can see the domain, all real, good there. There's no asymptotes because there's no values at which this isn't defined. And then the y-intercept, you plug in x is 0 and you get 0, 0 is the y-intercept. Then for the x-intercept, you set this equal to 0 and solve, and you get plus or minus 5.196, 0. My favorite number, actually. Okay. Okay, sweet. Next thing we're going to look at intervals of increase and decrease. So find the derivative of this, and you're going to get f prime of x equals x to the 2/3 minus 1 all over x to the 2/3. Sweet. So now we set that equal to 0, and now we solve that, and then we get x equals plus or minus 1 as the zeros, but we're also going to have 0 as one of the critical numbers, because if you have 0 here, this whole thing is undefined and can't have that. For the step, we're going to set up intervals using the critical numbers that we found, and then test a value by plugging it back into the derivative on each of those intervals and looking at the signs. So here we get it is increasing on -infinity to -1, decreasing on -1 to 0, decreasing again on 0 to 1, and increasing on 1 to infinity. So now we can use that information to do our third step, which is look for local maximums and local minimums. So if we look at this, we see, okay, the slope is going up here, and then at -1 it goes down. So that looks like it's going to be a local max. So then we can do -1, 2, because that's what you get when you plug -1 into the original equation. That's the local maximum. And then local minimum, well, we'll get this, negative to negative, so that's not a local maximum or a minimum. But here goes from being negative slope to positive slope. Cool, that's going to be a local minimum because 1 is at the bottom of that. So 1, -2 as our local minimum. Finally, we are going to look at concavity and points of inflection. So to look at the concavity, we're going to do the same thing that we did in step 2, except with the second derivative. So we find the second derivative, 2x to the -2/3 x to the -5/3, and then finding the critical numbers, we get x equals 0, and then we set up an interval of -infinity to 0, 0 to infinity, and then we test a value. So for example, you can test -1, plug it back in there, and you get a negative number, and you could test a value from here, for example, +1, plug it in here, and you would get positive values. So that tells us that it is concave down here and up here. This is what the final product of the graph should look like. As you can see, it's increasing from -infinity to -1, like we solved for, decreasing from -1 to 0, and additionally decreasing from 0 to 1, then again increasing from 1 to infinity. And also we see the concave is concaved down all the way to 0, then concaved up to infinity. So yeah, that's how to graph the sketch of a curve using derivatives, second derivatives, and all that fun stuff. I hope this helped. Finished! Probably cut that out.